Episode: Data Optimization is King. All about data design and optimization secrets. Well, we have covered a lot of my, potentially old school tech and software development and management ideas. We have a few more techie episodes remaining to go through before we'll resume the more storytelling tales of my adventures. And so, in this episode, let's talk about data design and optimizing data. So, let's talk about data and what data tells us about everything. Much like in business, which says follow the money to know the business, to know what's really going on. Here in tech land, we should also say follow the data. Follow the data to know what's really going on in software. Follow the data to know everything. This is true of engineering, programming, and hacking and cracking. They're all the same. The data, follow the data. It will tell you everything. Diving into code can feel overwhelming. Where do you start if you have not been the author of that code? Like a ball of yarn, search for and find an end or a start of data and begin unspooling and unthreading it. Follow the data. It will lead you through the code and everything that matters to it. As a hacker and a cracker myself in my life, there was always the Star Wars-like force that relied on vast knowledge and intuition, that I could pull the end of the ball of yarn and follow its thread, weaving in and out throughout its knotty yarn ball. Eventually, the knotted ball of yarn would be straightened and understood. You will have unwound the ball of code yarn using data to do so as your map. And like at the yarn's end, following the data through the morass of knotted, tangled code, the data will lead you through the valley of darkness, and the data will reveal what the code actually does, what it actually is. So I say again, follow the data to know the code. Well, on to another topic. Let's talk about optimization, baby. Let's talk about optimization, baby. Alright, I'm not a singer, but I tried. Seriously, however, optimization is an incredibly valuable thing to do, no matter how fast your computational power is or how vast your data storage capacity is. Before delving into this, I give you a warning, listener. This is, going to be very intense, even though it is at a high level. It is much like the other techie episodes. So, with that disclaimer, on all things optimization. Yes, optimization makes everything faster, smaller, and better. So let's get going. Data optimization is the king, whereas code optimization is the queen of optimization. As mentioned, this episode will focus on the king, on data optimization. The next episode will focus on the queen, code optimization. But fear not, there will yet be 2 more techie episodes following the queen of optimization. So, products can be made substantially faster through profiling and code refactoring and refinement. And we will talk about that too. But data design can make or break performance in any and every situation. So, let's talk about data optimization. Data optimization is king. Data design is huge. Data design affects client and server software. It affects memory and storage requirements. It affects processor and coprocessor performance. It affects networking, internet performance, latency, bandwidth, everything. Smaller data means less memory is required. That means less data must be moved, which means much faster operations and the ability to operate on leaner platforms. Design your data structures to be the smallest possible, thereby reducing the amount of data that must be physically read, written, manipulated, and likely rewritten and reread countless times. The less data that must be operated on and loaded and stored and transferred will make local machines and network traffic and cloud operations, each and every one, faster. Data packing can include things like combining literal bits of data into nibbles. That's half a byte of data, into full bytes of data, perhaps moving those into words, which are 16 bits or 2 bytes of data, or double words or longs, which are 32 bits of data, or double long, 64 bits of data. You get the idea. The concept here is smash as much data into the smallest, standard processor relatable data elements and structures possible. It will yield remarkable value and results. There's another method of data optimization just in data structures. It's called data proximity. It means related data is stored physically nearby, which improves the performance from the utilizing microprocessor, which utilizes a thing called read-ahead buffers and caches. So by using a read-ahead buffer, the processor reads more data than it actually needs in that moment, and it stores that in a very fast block of memory called a cache. So data proximity can become very difficult, however, to implement. I have found examples that data proximity can be very difficult with class and object inheritance, but it can be done. You can at least control the structures that you create and those that you use within your tight loops or recurring operations. You can even copy class structures that you do not have control of their data structures into a new, small, packed, controlled structure within tight loops. Minimally related data within the context of a class should be stored near each other in the local or inherited class data structure. This will allow the processor to load at least as much, if not all, related data in a single read, because the target data and the surrounding data will have been read at one time by the processor in its read-ahead cache line. It makes the other data reads free to the microprocessor. Note, there are different levels of caches that you might need to be aware of. There is immediate processor registers. They're not caches per se, but they're internal. They're inside the microprocessor or processors. They are immediately and as fast as access as anything the microprocessor can ever do. Then there is the processor internal high-speed cached lines of RAM. Those are literally blocks of memory that if you were to read 1 byte of data, oftentimes 2048 bytes or more of data will have been read with one data read fetch. That means every byte or block of memory beyond that 1 byte is free because it's already been stored in what they call a cached line of memory. Let's continue. There is also a cache called memory transit bus caching or caches. These are potentially numerous. There are numerous bus architectures as well. We're going to skip that in this episode because frankly, they're very deep in detail. So my point is here, we're going to talk about leveraging bus caches. Next thing, there are read and transfer buffers. These are not specifically caches either, but they are often very high-speed storage areas, typically used in between devices and chips that maximize specific hardware. So for example, you might have a cache from a medium that you read from, like a DVD, or perhaps a special cache that network downloaded data packets have been stored in. And then when your operation is ready to go, it has much faster access to this very critical data. Another thing that's quite critical to be aware of in data structures is data alignment. Aligning data according to native microprocessor fetch sizes and its cache lines will translate to less data fetches by the processor and its pipelines, thereby maximizing the processor's read-ahead instruction and data cache lines and ability to operate on data that's already been read. It may be necessary to even pad data structures with miscellaneous, filler, irrelevant data, or even leave it as just wasted, unused areas of memory, in order to increase the speed of an operation so that it is cache-aligned on cache-lined data. Minimally, identify structures that are reused in rapid succession, such as inside a very tight loop or a frequent recursive call, and pack and align data that they use so they are processor cache-friendly, memory aligned. Not every system provides it, and frankly, not every API or SDK will give you access to it. But let me talk about Direct Memory Access, or DMA. It uses special hardware operations to mass replicate blocks of memory, often moving them from one memory space to another memory space. For example, you might want to DMA a huge block of memory from normal RAM into video RAM. Let's talk about some details. DMA data copies operate independent of the normal processor operations or operand fetches. DMA moves huge blocks of memory at one time. DMA alone is not a magic bullet like it might sound. It may sound free, but it's just another very powerful tool in the tool belt of low-level controls often used by firmware engineers. To maximize DMA benefits, organize your data in DMA-friendly block sizes and memory address alignments. It can make an incredible difference in direct memory access performance. Again, an example of DMA between memory spaces might be direct memory access transfers from the CPU, random access memory RAM, to GPU, graphics processor unit, video RAM or VRAM, or perhaps from an interim memory block area such as a network data packet buffer block or DVD read-ahead buffers. You get the idea. It's the idea of moving from one entirely separate memory space, controlled perhaps by an entirely separate processor, into another's. There is so much to optimizing data and talking to it in a podcast. It is undoubtedly extraordinarily hard to grok. My hope is that this somewhat high-level technobabble about optimization has offered some useful ideas, at least about optimizing data.